Every single time you turn on your tap, you're interacting with a massive hidden world right beneath your feet. Welcome to this explainer. Today, we're embarking on a pretty fascinating journey. We're going to start by looking at the massive, almost incomprehensible scale of our global groundwater systems. Then we'll zoom all the way down to microscopic molecular chemistry to understand how water actually works. And finally, we'll zoom back out to look at real-world pollution, how it travels underground, and what ultimately happens to it.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the world's hidden ocean, explore water's molecular magic, and figure out measuring quality and solutes. Then we'll look at sources of contamination, trace contaminant transport and fate, and wrap up with protecting our groundwater. We're smoothly shifting from macrogeology right down to microchemistry.
All right, Section 1, the world's hidden ocean, and the sheer scale of our groundwater. To truly get groundwater, we've got to grasp the massive global stakes we're dealing with here. We're not just talking about some muddy puddles under the dirt. Groundwater is literally the most abundant available source of fresh water, and remarkably, it's the most extracted raw material on Earth. Get this, 97% of the planet's non-frozen fresh water is sitting right beneath our feet. The scale of our reliance on this hidden ocean is just staggering. We are withdrawing something like 982 cubic kilometers every single year. Just imagine a river the size of the Amazon flowing continuously, completely out of sight. We pull this up nonstop to sustain life, which means the quality of this water dictates the safety of the food we grow and the literal tap water we drink every day.
Moving on to Section 2, water's molecular magic, or the science of solvents.
So, what actually determines that water quality? Well, to answer that, we have to zoom way in, down to the microscopic level to see exactly why water interacts with the surrounding earth and pollutants the way it does. Check out this classic H2O molecule. You've got your oxygen atom and your two hydrogen atoms. You know, it actually looks a bit like Mickey Mouse. And believe it or not, that specific shape is absolutely crucial because it creates an asymmetrical electrical charge. The hydrogen ears carry a slight positive charge, while the oxygen chin is slightly negative. Because of this funky, unique geometry, hydrogen bonding causes these water molecules to naturally clump together in clusters.
In science, we call this a polar molecule, and honestly, this is the secret to everything we're discussing today. Because that charge is uneven, this polar nature acts exactly like a tiny magnet, and that magnetic property is what makes water an incredibly powerful and highly effective solvent for basically any other ionic or polar molecules it bumps into underground.
And this brilliantly illustrates exactly how that works in practice. Notice how the unique angle of the water molecule acts on its surroundings. When water meets natural groundwater solutes, which usually carry a charge, either as positive cations or negative anions, the polar water molecules literally physically arrange themselves to surround those charged ions. The water molecules orient themselves in strict accordance with the charge of the ions they're dissolving, just completely enveloping them.
Which brings us to Section 3, measuring quality and solutes, or what's dissolved in the deep. Now that we know how these tiny molecular magnets work, let's see what happens when they wash through the earth. Because water is such a fantastic solvent, natural groundwater is essentially a giant complex mineral soup. It naturally dissolves common subsurface rocks, things like calcium carbonate, magnesium carbonate, and sodium chloride, which are super soluble. They dissolve directly into the natural groundwater, filling it with ions like calcium, magnesium, sodium, and chloride. Now, this is a completely natural process, but we still need a way to measure exactly how much of this solid stuff is swimming around in our water.
So, how do we do that? We systematically classify water quality using a metric called total dissolved solids, or TDS. Basically, TDS represents the total amount of solids, measured in milligrams per liter, that get left behind when you completely evaporate a sample of water until it's bone dry. To put that into everyday perspective, fresh drinking water from your tap sits on the very lowest end of this scale, under 1,000 milligrams per liter. On the flip side, ocean water sits way down in the saline and brine categories. Brine actually represents water with over 100,000 milligrams of dissolved solids per liter.
But here's the catch. Evaporating water to dryness in a lab just to measure TDS, it takes a massive amount of time. So scientists use a pretty brilliant shortcut. Instead of boiling it, we measure electrical conductivity, or EC. Remember how we said those solutes in water carry an electrical charge? Well, because of that, water's ability to conduct electricity serves as a highly reliable inverse measurement of its dissolved ionic solutes. So by measuring the EC and multiplying it by a constant of roughly 0.6, we get a super accurate immediate estimate of the total dissolved solids. Pretty clever, right? Next up, Section 4, Sources of Contamination. How pollutants actually enter the system. Up until now, we've only talked about natural minerals, but let's zoom back out to the macro level. How do human activities introduce artificial contaminants into these delicate, highly solvent underground aquifers? Well, two of the heaviest industrial threats come from mining and landfills. Mining generates non-ore-bearing waste rock, tailings packed with crushed rock and trace metals, and highly polluted mine water. Meanwhile, landfills produce a dangerous and, frankly, pretty gross substance called leachate. When rainwater washes through municipal solid waste, it acts as that powerful solvent we talked about earlier, creating a highly toxic, polluted liquid that can seep directly down into the soil if we don't aggressively manage it.
And here's the scary part. The pollution doesn't just stay put. It creates an absolute logistical nightmare of transport pathways. Contaminants can move from soil to water through leaching, runoff, or erosion. Just think of agricultural pesticides washing into nearby streams. But they can also move from soil to air through volatilization, where compounds literally evaporate right off the dirt into the atmosphere. They can even move from water to air through aerosol formation. It makes environmental cleanup incredibly complex. It's literally like chasing a moving target across soil, water, and air.
Let's move to Section 5, Contaminant Transport and Fate, or the Journey Underground.
Now, what's really interesting about this is the ultimate mystery of hydrogeology. Once a contaminant is released from a factory, a farm, or a landfill, where does it actually go? What happens to it down there? Well, its journey is governed by three primary mechanisms. First, there's advection. That's the physical transport of a substance by the bulk flow of the groundwater itself, kind of like a contaminant riding an inner tube down a flowing river. Next is diffusion. That's the chemical process where contaminants spread from areas of high concentration to low concentration, like a tea bag steeping in a totally still mug of hot water. And finally, dispersion. This is the scattering of the contaminant because of the complex, uneven pathways it has to take around grains of soil and rock. It's basically bouncing around like a pinball through a maze. These three forces totally dictate how pollutants spread.
But the contaminants don't always move freely. This is where we introduce a really vital concept, the retardation factor, or R. This factor quantifies the extent to which contaminants physically stick to the soil particles as they flow by. Imagine throwing a sticky Velcro ball through a tunnel completely lined with Velcro. It's going to get slowed down fast, right? A higher retardation factor means contaminants have a high affinity for the surrounding rock, dramatically slowing down their underground migration compared to the water flowing right past them.
You see, transport isn't a one-way street. It's a continuous push and pull. Sorption is the process of those pollutants sticking to the subsurface surfaces, while desorption is when they unstick and release back into the water flow. And thankfully, nature has its own hidden cleanup crew down there. Biodegradation by microscopic underground organisms can actually consume and permanently break down some of these contaminants, completely altering their ultimate fate.
Finally, Section 6, Protecting Our Groundwater, the final challenge.
All of this complex chemistry and hydrology leads us to the final, absolutely crucial challenge. We have to connect the scientific fate of these contaminants back to the urgent need for environmental protection. Figuring out where a contaminant ends up relies on understanding all these complex interactions we just covered: sorption, chemical precipitation, hydrolysis, biological transformation, and those preferential flow pathways underground. Understanding these processes isn't just some academic exercise. It is literally the difference between safe drinking water and a public health crisis. It's what allows authorities to develop accurate risk assessments and effective pollution prevention strategies.
So the ultimate question becomes this. When a hidden aquifer is tainted, do we step in, spend millions, and actively pump and treat it? Or do we trust nature's own processes, like sorption and those hungry microbes, to heal the waters over time through natural attenuation? The molecular magic beneath our feet gives us the power to protect 97% of our planet's freshwater, but only if we truly understand how it works. Thanks for joining me on this explainer, and I'll see you next time.